And the next thing we're going to add is Faraday's law, because Faraday's law tells us how changing the magnetic flux through a loop will end up inducing a current. So electromagnetic induction is basically the concept that's being described by Faraday's law. So what Faraday's law does is it describes how changing the magnetic flux through a wire loop will cause currents to flow in that loop. Now, so here's kind of just sort of breaking it down. The magnetic flux we've defined before, that tells you how much the magnetic field is piercing the surface of your loop. When you change that, what that does is that induces an EMF. So basically that's going to induce a potential difference. That potential difference is going to drive a current. So we'll talk about that as inducing a current. So this is basically the way electromagnetic induction works. You change the magnetic flux. That's going to induce an EMF, induce a potential difference. That potential difference will then drive a current. And again, this is just a reminder. EMF, electromotive force, voltage, potential difference, all these are the same thing. Alright, so mathematically, what Faraday's law says is that the induced EMF can be calculated this way. So the minus sign we'll come back to in a second, but we're largely going to ignore the minus sign in terms of this calculation. We're just going to worry about the magnitude of the induced EMF. So we'll tend to deal with this in terms of absolute value signs. What the minus sign's telling us is that the induced EMF is going to try and resist the change. So the way that you're going to change the flux, you're going to induce an EMF that tries to resist that change in the magnetic flux. That's what the minus sign is basically telling you. The N is just the number of loops that you're dealing with. So you got a single loop, N is just one. You got 100 loops in your solenoid, N is going to be 100, whatever it is. And then you're interested in the change in the magnetic flux with respect to time. Now again, if we have a constant field through a flat loop, then we said we can calculate the magnetic flux this way. So this is a simplification. We won't always be able to use this, but there's a lot of the scenarios we will look at. We'll be able to deal with the magnetic flux in terms of magnitude of the magnetic field times magnitude of the area of the loop times cosine of the angle between the field vector and the area vector. And again, we're interested in taking the derivative with respect to time of that. So part of what sort of working through Faraday's law problems for us is in some sense going to be about, it's going to be about identifying what is changing in the magnetic flux. And basically we've got three options. So either you're changing the strength of the magnetic field, or you're changing the area of the loop within the magnetic field. So this may be a situation where if I have a loop that's entering a magnetic field or leaving a magnetic field, or in some situations where I can shrink the loop, enlarge the loop. So I can change the area of my loop, or I can change the angle between the area vector for my loop and the magnetic field. So these are basically the things that we're going to end up changing. So as an example, Faraday's law when the magnitude of the magnetic field changes. So here's a situation where, say, what I've got is I've got a constant magnetic field being generated by my magnet here. I've got a loop within that constant magnetic field, and then all I simply do is choose to increase or decrease whatever the field strength is. So this is effectively a variable magnet that I've got set up here that I can change the strength of the magnetic field. So what's going to happen is, well, I'm not changing the area of my loop, that stays the same. I'm not changing the relative angle between my loop and my field, so these things are constant, and I can pull them out of the derivative, and so what I'm left with is just dB dt, because B, the field strength, is really the only thing that's changing. And again, here's the way that we're going to tend to deal with this. We're just going to worry about the magnitude of the induced EMF, and we'll really pick up this minus sign by talking about Lenz's law, and we'll have some right-hand rules that will help us do that. Another example, in terms of just changing the magnetic field, could be that, well, again, here's my loop, and I'm going to keep it just sitting there. but what I might do is choose to move a bar magnet towards it or move a bar magnet away from it. So as I move my bar magnet, again, what I'm doing is I'm changing the field strength through the loop. So area of the loop stays constant, relative angle stays constant, B is the only thing that's changing. So the second option I got is that I can change the area of the loop. Well, I can either change the area of the loop itself. So what I have here is I basically have a U-shaped metal piece, and then I've got a second metal bar that comes across. So this gives me a pathway to complete this gives me a complete pathway for current to flow around. But as I start moving this, say moving this bar to the right, then you'll notice what I'm doing is I'm increasing the area of my loop, right? I'm making the rectangle bigger, which means I'm increasing my magnetic flux. So this would be a situation where by moving this bar around, I'm actually changing the area without doing anything to the magnetic field or anything to the relative orientation. So in that case, now I can pull out B, it's constant. Again, the relative angle between the magnetic field and my area, they're constant. So these things I can pull out of the derivative, and I'm left with dA dt. Or what I might do is I might not change the area of the loop, but I'll change the area of the loop that's in the magnetic field. And so one way to change the area of the loop is literally to change how big the loop is. The other way to change the area of the loop is to change how much of the loop is in the field. And so this will be a second situation in which, again, what I care about is dA dt. That's really the piece that's changing, that's causing the magnetic flux to change. Last option is I might do something like this. So here again I've got a simple rectangular loop. I've got a constant magnetic field, but I'm spinning it. So in that case what I'm changing is not the area of my loop, it's not the strength of the magnetic field. In fact, what it is it's the relative orientation between the loop and the field. So this would be a situation where this cosine term is actually what remains within the derivative, and so I'd have to deal with that. So this is really going to be the crux for us of working these Faraday's law problems, is going to be identifying which of the three things, assuming we've got a flat loop and a constant field. So which of the three things under that case are we changing, and so then what do we need to keep track of, or what needs to still be within the derivative so we can take its derivative with respect to time. So that's the way we're going to figure out what the induced EMF is, and then again we'll be able to use Ohm's law to say, well, now that I know what the EMF is, well, that potential difference, that's just like V, that's going to be IR, so that'll help me figure out what the induced current is. Right? So we'll use Faraday's law to figure out what the potential difference we're inducing is, and then use Ohm's law to figure out how much current that induced potential is able to drive. And that's going to be the real crux of what we're doing with electromagnetic induction.